Welcome! Today we're here to talk about logistic regression. This video series was prepared to you from Mitch Borgert, Martin Eong, Lindsay McPhillips, John Morgan, and Kelso Kwan. The contents of this series is that we will have a video on introducing logistic regression, which is the video that you're currently watching, applying logistic regression to create a simple, well-fitted model, and then to apply logistic regression to a more complex model, as well as the diagnostics for the linear logistic regression model. And note, R&R Studio was used to do the diagnostics, model fitting, as well as conclusions. So logistic regression is a technique used to model data when the response or subject that you're interested in is a binary response. Now, this could be either coded as 1 to 0 or true or false, but it can really be for anything where one part of the data is and one part of the data isn't. Is the car a hybrid? Is it not a hybrid? Was it sunny that day? Was it not sunny? And logistic regression uses the same ideas as linear regression in that it has one response variable, which will be the y, and the model can have one or more independent variables, which are your x, and then there will be beta coefficients to go along with those x's. When modeling an event with probability 0 or 1, the graph of the regression equation is generally considered to be an S-curve, where you see over the course of the x predictor, the probability of y eventually goes up to 1, and usually in a relatively rapid fashion. And here you see a nice little graphic where you have a linear model that's going through the line, but if in fact it's logistic data, it may be better to fit your data along that S-curve. It would be more telling than just having it be that straight line. The main assumptions for logistic regression model is that the dependent variable must be categorical, all observations need to be independent, and that goes with any regression, and there also needs to be minimal correlation amongst the independent variables. There also needs to be a larger sample size than your typical sample size required for linear regression. So since yi is a binary response with form 1 and 0, yi can be considered to be a Bernoulli random variable. So when yi equals 1, the conditional probability is easily modeled as the probability density function of the logistic distribution. In the case of simple logistic regression, the conditional probability statement will take the same form as the logistic PDF as seen in this first equation, except you can replace the exponent from the PDF with beta naught and beta 1x for simple logistic regression. Now, in order to make this a little easier to digest, we'll bring up the discussion of the odds of the event, which are defined as the probability of the event happening divided by the 1 minus that probability. When you set p in that odds equation to the conditional probability as defined above, you transform the conditional probability into the odds function, and it becomes much easier to deal with in that it's simply the exponential term to the simple logistics equation in that exponent. So now we're going to talk about the odds transformation. As you can see on this slide, we have our simple logistic regression function. Now, when you transform this using the odds formula as defined as p divided by 1 minus p, if you set that p equal to your function in the simple logistic regression, you get a much more easier to deal with output in that the odds of our logistic regression equation is just the exponential term to the beta naught plus beta 1x1, something that you'd expect to see in linear regression. So now from there, you can just take the log of that function and you're just left with the beta naught plus beta 1x1, which is it's the model for linear regression, and so the log odds transformation is a way in which you can take logistic data and get an answer that will be in a linear fashion. And it's worth noting that one unit on the log odds scale is referred to as a logit. So in looking at the difference between yi at two different times, at xi and xi plus 1, we're able to break down the meaning of the exponential term to the beta 1. So you might want to pause the video right now to check out this proof, just so you don't have to do it in live time. But anyways, what we get here is when you take the odds from xi being at x plus 1 and minus the odds of xi at x, you get that the difference is e to the beta 1, meaning as y goes from x to x plus 1, the beta 1 is the multiplicative increase in the log odds from xi to xi plus 1. And so here's an example that might help make this make a little more sense. If you are modeling the hours of studying for the comprehensive exam onto whether or not the student passes the test, the exponential term to beta 1 would be the increase in the odds of passing the test when the student has an additional hour to study for the exam. At the same time, you could also use the logistic regression curve to see when additional studying would result in highly diminished increasing odds. In other words, it'd be time to stop studying, which would be as the logistic curve goes to 1. And this definition also works for any beta in your model if you had more than one independent variable used. So now, for logistic regression, the beta naught term is very similar to that in the linear regression in that it's sort of like the intercept. So in our case, the exponential term to the beta naught is the odds of what you're categorizing by y given that x equals 0. So to put that in terms that make a little more sense, in the previous comprehensive exam example, exponential term to beta naught would be the student's odds of passing the exam without having studied at all for it. So as you can imagine, extremely close to 0. If you have a simple logistic model where x is coded categorically with a 1 if a student received an A in all SDSU statistics core classes, being 610 and 670 A and B, and a 0 if not all A's in those classes, and the Y as the outcome of the student's comprehensive exam, one would expect an odds ratio greater than 1 because there should be a positive relationship between receiving A's in the core classes and passing the exam. Conversely, if X was coded as the amount of lectures missed by a student for their core classes, then one would expect an odds ratio less than 1, signifying a negative relationship between missing lectures and passing the comprehensive exam. Some of the main differences between logistic and linear regression are that graphing logistic regression yields an S-curve instead of a line for linear regression, and that logistic regression is concerned with the probability of an outcome, while linear regression is concerned with the value of that outcome due to its continuous dependent variables. Logistic regression requires a categorical dependent variable, while linear regression requires a continuous dependent variable. The conditional expectation of the dependent variables in logistic regression is distributed as Bernoulli random variables, whereas linear regression continuous variables are distributed as normal random variables. So, to close out this introductory video for logistic regression, we're going to go over a few of the main differences between logistic and linear regression. Now, obviously, logistic regression differs from linear in that we're dealing with a binary outcome for logistic regression. Now, linear regression also requires a continuous dependent variable. And logistic regression is concerned with the probability of the outcome rather than the value of the outcome, as linear regression is. And graphing logistic regression tends to yield more of an S-like curve, while linear regression yields a line, hence the name